Hi, Math 82 students. Today we are going to be talking about separable differential equations. So we are right toward the beginning of class. We are going to start here in this world. And let's get to the first slide. Let's first define what it means to be a separable differential equation. A separable differential equation is a first order equation. So it's important that it's first order that can be written as a product, not a sum, of two functions, one that's purely a function of the independent variable t and one that's a function of the dependent variable y. So in this case, let me write this here, we have y prime of t, which equals dy dt, can be written as a function of y by itself and multiplied by a function of t, which we'll call h of t. The great thing about this is that the differential equation can be either linear or nonlinear. That's a big deal because nonlinear equations are often pretty hard to solve analytically. In other words, it's hard to find a closed form solution to those. So when you have a first order differential equation that's separable, it doesn't matter whether it's linear or nonlinear. We have ways to solve it. Let's first look at some examples of separable differential equations. In this first example here, I'll call this one, we are solving for y of x. Solve for y of x. So y is now a function of independent variable x. And we can see which part of the right-hand side plays the role of g of y and which plays the role of
h of x.
So here is my function g of y. That's just equal to y. My function h is a pure function of x. So this is my h of x. So this is a nice separable equation. Let's look at the second example. This second example is actually one that can be separated in more than one way. Here we are solving for function p of t. And it turns out that there's not a unique way to separate this. This, by the way, as an aside, is the classic equation for logistic population growth. Logistic population growth, and we know that it has a solution that looks a lot like this S-shaped curve. And we'll come back to that and look more at that later, but I'm just giving you a preview of coming attractions. All right, for this right-hand side here, we can actually decide that we want our function of p to be the entire thing. Because if you notice, because the system is autonomous, that the independent variable t doesn't even show up. So the right-hand side can be my entire g of p, and then my h, what plays the role of h, that can just be the constant 1. But that's not the only way to do it. There is another way to do this. So sometimes these separations are not unique. Another way to think about this is to let our g, we're going to let g of p just be the part without the constant r. So that's going to be p times 1 minus p over k. And I can let h just be the constant r. So t doesn't show up anyway, so I can actually choose h to be 1 or the constant r. The key to understand here is that this is an autonomous differential equation, and autonomous equations are always separable. So that's good news. All right, let's look at the last example. The last example here, we're solving for y of t. So y prime now represents y of t. And in order to solve for this, we do just a little bit of a rewrite in order to see that it's separable. And we see that y prime is t times 1 plus y squared. And so we can quickly see that 1 plus y squared is playing the role of g of y, and t is playing the role of h. That's my h of t. Okay, so those were all examples that were separable and worked out well. What's an example of a non-separable differential equation? How about this? dx dt, we would be solving for x of t is x squared, that makes it nonlinear, plus tx, that makes it non-autonomous. And let's throw in another term for good measure, e to the x, nonlinear, non-autonomous. This thing, if we want to categorize it, which is always a good idea to do, this is first order. It is nonlinear, as we saw. It is non-autonomous. And it is not separable. Not separable. So that's an example of one that we cannot solve using separation of variables. Okay, if you've had Physics 24, you will have seen this before. You've seen how to go through the process of solving these, and there's a slight abuse of notation. I will point out this is a screenshot from Physics 24 where you are told that you have to be dealing with first order differential equations, and they are separable again if you can separate the right-hand sides into a function of the independent variable and a function of the dependent variable. Okay, so in Physics 24, you saw an f and a g. Here we're doing a g and an h. But essentially what you do is you treat the left-hand side, dy dt as a fraction. It's a slight abuse of notation, but we're going to see later in class why this is okay. And you move the dt over here, and then you take your g of y and you move it down here to the left, and then you throw integral signs around everything and integrate to your heart's content. Let's look at an example of how that works. Next page. Here is a first order separable ordinary differential equation. So again, first order. This is linear. It is non-autonomous. Why? Because we see the t showing up explicitly. Since it's linear, we can ask whether or not it's driven. So it is driven. And remember that one of the tests for that is if you try plugging in the solution y equals 0 and it works, it's not driven. But if you plug in y equals 0 and it doesn't work, then it's driven. So that's the case here. And it turns out this is also separable. Good news. All right, so let's take dy dt equals t y minus 1. So I'm doing a slight rewrite just to see that it is obviously separable. And we're going to take our function of y alone and move this down into the denominator, and our function of t alone and move that, keep that up in the numerator. So in fact, what this turns into is dy over y minus 1 equals t dt. So I've taken this dt and moved it over here. Pardon me, I misspoke before. And I've taken this y minus 1 and moved it up here. And then I'm going to integrate both sides. Okay, because of all that, I'm just going to rewrite this again, just to be clear. All right, now we can start integrating, but be careful. There is one small possible pitfall here, and many of you may have noticed this. I've got a y minus 1 on the denominator, and that is a place where you have to be careful. Anytime you might accidentally divide by 0, be careful. So what I'm going to say here is be careful. Let's assume just for now, because we're going to come back to this later, that y is not equal to 1. And later we're going to come back and see, is it really true that y can't be equal to 1? Or is this just something that we have to kind of skirt around because of our solution approach? And then we can look at the y equals 1 case separately. All right. On to integrating both sides. Integrating y dy over y minus 1 leads to natural log of the absolute value of y minus 1. Don't forget absolute values. And integrating t gives us 1/2 t squared. What else should we not forget? Don't forget the constant of integration. Okay, now remember that I'm integrating now in the indefinite form because I don't have limits of integration, but you could integrate in the definite in a definite form as well. So I'll just put a note here. Note, integration could be indefinite or definite. But if it's indefinite, always remember your constant of integration. That will end up being important. Okay, now we're in a position to solve for y. So of course, we've got a natural log. Let's exponentiate. So solve for y. And we're going to exponentiate. So let's see. So we've got y minus 1. I can't pop off the absolute values just yet. Equals e to the 1/2 t squared plus a constant, which of course I've got e to a sum of things is a product of e to the things. So that's e to the 1/2 t squared times e to a constant. But what's e to a constant? That's a constant. In fact, it's a positive constant. So I'm just going to call that d, e to the 1/2 t squared. And in this case, d is e to the c, and that whole thing has to be positive for now. That's not going to be a problem because watch what happens. Now I'm going to take the absolute value signs off. So y minus 1 without the absolute value signs is plus minus d e to the 1/2 t squared. But with a plus minus positive d, why don't I just call it something else that can just be plus minus? So I'm just going to call this, let's give it a new name, f. Let's call that f, e to the 1/2 t squared, where f is some constant, and it can be either positive or negative. No constraints on it whatsoever. Okay, so I can actually leave that in this form. So we can write y minus 1 equals f e to the t squared over 2 for now, or we can write y equals 1 plus f e to the t squared over 2. I'm going to hold off my decision on that until I've decided what f should be, because right now we actually have a family of solutions. If you remember, because I've got this constant f, this represents a whole family of solutions. A whole family, of solutions. Okay, and the only way I can narrow it down to one particular solution is if I also impose an initial condition. So let's suppose we have an initial condition. Y at time 0 is some known number. So y naught is going to be some real number. You can also write y naught is real. So there's our notation. Okay, so what does that mean? At time 0, our function y of t, remember this is really a whole function of t, our function y of t reduces to this particular constant. So this means that when t equals 0, y of t equals 0 is just this y naught. Okay, so let's let t equal 0. Let t equal 0 in our solution up here. And we have y of 0 is going to be, what happens when we plug in t equals 0? That's 1 plus f e to the 0. Okay, so that's just 1 plus f. And that whole thing we've been told is y naught. So now I know what my unknown constant f is. So f is simply y naught minus 1. Okay, so that's now been fixed by my initial condition. So my entire solution to the initial value problem, IVP is shorthand for initial value problem, is as follows. I'll put it in a different color. Y of t is 1 plus y naught minus 1. That's my f e to the t squared over 2. And just to remind us, that's my f right there. So that's my entire solution to my entire initial value problem that has been solved using separation of variables. All right, now, while we were solving the differential equation, we said y itself, the solution can't be 1 because we didn't want to divide by 0. But could it be 1? So what we want to do is we want to look at the original differential equation and decide what y could actually be. So let's look at the original ODE. That was y prime equals ty minus t, and ask the following: could y of t equal 1 be a solution? So we're not rewriting the DE now. Now we're just looking at the original and just asking about y of t equals 1. So let's suppose it is. All right, so suppose y of t equals 1. So I'm handing the function y of t is 1. Plug it into your DE and see if it satisfies the differential equation. As simple as that.
So if y of t is the constant 1,
and the derivative is 0. So in the ODE, which is this, my left-hand side, y prime equals 0. My right-hand side, plugging everything in, is ty minus t equals t times y is 1 now, minus t, which is 0. So 0 equals 0, so everything fits. So therefore, the left-hand side equals the right-hand side. So y of t equals 1 does satisfy the ODE. Hooray. Okay, so y of t equals 1 is actually going to be fine. And it turns out that if I had given you the initial condition that y of 0 is 1, then my entire solution is going to be y of t equals 1. So I'm just going to put that quickly here. So note, if your initial condition is y of 0 equals 1, then the solution to the initial value problem is going to be y of t equals 1. So it turns out it's the constant solution in that case. All righty, let's look at what that means in summary. So the initial value problem we solved, this whole thing, a differential equation with its initial condition is called an initial value problem, or IVP for short. And we've shown so far that the solution looks like 1 plus y naught minus 1 e to the t squared over 2. And remember, this was our constant f. That was a constant. Now we want to make sure it satisfies the whole initial value problem. So it's important to always check your work. Always check your work. And you can do it, because if I've written down a solution, all you have to do is plug everything back into the differential equation and the initial condition. So if you check the differential equation, take my solution, y prime, plug that in, okay, and you take the derivative of 1, that's 0, so that works out. You take the derivative of my y naught minus 1 e to the t, this whole thing here, and that gives me that with that. That's just taking derivatives.
Now we check that the derivative of our solution actually satisfies the differential equation. So take our solution and plug it into the right-hand side of the differential equation. T times y gives us t times quantity y naught minus 1 times e to the t squared over 2. And then minus t, we add that. And then you see that the t and the minus t cancel. And indeed, the right-hand side of the differential equation equals the derivative of the solution we found. So our solution satisfies the ODE.
Now let's check the initial condition, and you plug that in. And in fact, when you plug in time equals 0, you get your y naught back. So everything actually works. So this works for all y naught. So again, I can't emphasize enough how important it is to always check your work. Okay, so we've seen what it looks like to be a separable differential equation. We've looked at this example, how you would solve a separable differential equation. And when we come to class, I'm going to stop here. And when we come to class, we're going to see why this method of treating my dy dt like a fraction over here, treating it like a fraction, even though it seems maybe a little seems non-rigorous, it actually is covering up some manipulations that are in fact rigorous mathematics. So we're going to see that when we come back, and we're going to start here with those notes. All right, see you in class. Take care, everybody.